Hello everyone. So today we have another example from a second order linear differential equation, homogeneous differential equation with constant coefficients. And specifically, we're looking at this physical system known as a harmonic or damped harmonic oscillator. Basically, you have a mass, a spring, and a damper. And we know the equation of motion for this system can be written as mx double dot mass times acceleration plus cx dot plus kx is equal to 0. And let's say that in this case, mass is equal to 1, c is equal to 4, and k is equal to 5. So for these values of these constants, let's solve this equation. So if we plug in those values, we get x double dot plus 4x dot plus 5x is equal to 0. And here, x is the displacement of this mass, and t is time, our independent variable. X is our unknown function, t is our independent variable. Okay, so we know to solve this equation, we're assuming a solution that's exponential, something like e to the mt. We plug that in the equation and we get the auxiliary equation. We get m squared plus 4m plus 5 equals to 0, right? So this part is called the auxiliary equation, and the roots of that will tell us the behavior of the system. So the roots of that auxiliary equation can be found using the quadratic formula. So we have 4 squared or 16 minus 4 times 5 or 20 divided by 2. Right? And now the problem is what we have under the square root, that's a negative number, right? Because this will be negative 4 plus minus 16 minus 20 divided by 2. And of course, negative 4, that will give us the square root of negative 4 gives us an imaginary number, which is 2i. And then we divide by 2, we get just I. So the two roots of the auxiliary equation, also known as the characteristic equation, will be negative 4 divided by 2, or negative 2, plus minus negative 4. Square root of that is 2i divided by 2 is I. So these are the roots of the auxiliary equation. So we know that once we have a solution with so remember, our solution is x is e to the mt, and now we just found m is a complex number. It has an imaginary part, and we know that in this case the general solution will look like this. You have e to the real part, that's the negative 2t, times some constant a cosine the imaginary part, which is 1. So cosine of 1 times t plus b sine of 1 times t. Okay, so this part is this is called the general solution. Okay, so again, the general solution so again, the general solution in this case will be displacement as a function of time is e to the negative 2t, because that's the real part, times a cosine of the imaginary part, which is 1 times I, so cosine of 1t plus b sine of 1t. So we're familiar with this formula. This is, and we derived this last time in class. So this is called the general solution. Why do we call this the general solution? Well, because this is not one solution. This is a family of solution. For any value of a and b, this will satisfy this equation, the differential equation of motion. So what is this specific problem we're trying to solve? Well, we need to know its initial conditions, okay? So let's go back to the problem statement and add that. Let's say the initial condition is x naught was 0 and x dot naught was 2. So what that means is that the spring and the mass is not displaced initially, but it's given an initial velocity of 2 meters per second to the right. Okay. So now that we have an initial condition, we can apply that to basically find a and b, the values of the constant. So the first initial condition says x at 0 has to be equal to 0, right? So if we plug in 0, we get e to the 0, which is 1, times a to cosine of 0, again 1, plus b sine 0, which is 0, right? So this has to be equal to 0. This term will be 0, this will be 1, this will be 1, and that gives us that a has to be 0. Okay, so that is our first constant value, coefficient value. Second one is that x dot at time 0 has to be 2. So that means I have to take a derivative of x, right? But the good thing is I know a is already 0, right? So I don't even need to worry about this term and taking its derivative. I just need to take the derivative of e to the negative 2t times b sine t. So that is negative 2 e to the negative 2t times b sine t plus b e to the negative 2t cosine t. And we plug in 0, and again, this has to be equal to 2. So if I plug in 0, I'm going to get negative 2 e to the 0, b sine 0, so this will be 0, plus b e to the negative 2t, or 0 cosine 0 is 2. Right, so this term is 0, this is 1, this is 1, and that gives me b is equal to 2. So we found the two coefficients, and finally our solution is e to the negative 2t times a, which was 0, so just b sine t, and b is 2. I'm going to put 2 before this, so we get 2 sine t, and that's the solution. So looking at this solution in the context of our problem, this is displacement versus time and displacement of this mass. So what's happening is you have two parts, right? You have the sine term, which basically tells you that your answer will have oscillations. This mass will oscillate. And this term, which tells you that the answer will decay exponentially. Okay. And this system where you have decay and oscillations together, this is called an underdamped system. So now I'm going to switch to MATLAB to show you this solution, the plot of this solution. Okay, so here I have this MATLAB script that will plot the answer. Again, the answer is 2 times exponential of negative 2t times sine t, okay? And when I plot this, what you see is that you're getting basically it's really hard to see any oscillations, right? And I can show you this video again. Really just see this go up and down once. And the reason for this is that the decay rate is pretty high. It's a pretty large value. If I made this, if we could somehow manipulate the parameters such that the answer would be 0.2t, the decay rate would be much slower, and it would be much easier to see that, okay, this is oscillating and decaying. Okay, and maybe we can run that for a longer time, so we're actually able to see that. Right, so for example here, right, so again, oscillating and decaying. Another good way of seeing just oscillations is if somehow, again, this is not the case here, you of course have damping, but if you didn't have damping, then you might get an answer that looks like this. And this is what kind of behavior? Well, of course, this is just pure oscillations. A pure sine function would look like this, right? So something like that. Run it for a shorter time. So that it's not so fast. Yeah. Okay, so that is our extra example from this section of the textbook. Very, very important concept. A very important section of the textbook, especially for us mechanical engineers. Again, the mass spring damper system, the harmonic oscillator is used everywhere, not only for a real mass spring, for a literal mass spring. It's the model for many, many physical systems. So that said, we're going to stop here and I'm going to share these notes with you and the MATLAB script. Thank you.